So this will be the last tutorials of COM 2711H, and I'll cover weekly problem set 10 and 12. So there's 2 problem sets. So for the first question, starting from week 10, we have to consider a sample space and to mimic a uniform distribution. And and it is given that an open interval AB is an event, and we set the probability of such events to be B minus A. And we know that the complement of an event is also an event, and the union of countably many events is also an event. And we want to prove that the closed interval AB is also an event. So to start, we can see that the closed interval AB is simply just the open interval union with A and B. Union with A and B. And we want to show that they are the same. So closed interval is actually the same. The probability is actually the same with open interval. So it's just left to prove that the singleton event A and B has a probability of 0. To see that, we can first define AN to be, so let's take A as an example. We can set AN to be the interval A minus 1 over N and A plus 1 over N. As N tends to infinity, we can see that this part goes to 0, right? So when it tends to infinity, this part goes to 0, and this interval actually shrinks down to a singleton event. And we have the singleton event to be the intersection of n equals to 1, and it goes to infinity, and such AN. And this is the singleton event, and the intersection, it's the singleton, the intersection of all these such AN is an singleton event. And as n tends to infinity, we have the probability equals to the intersection of all such AN, and this is 0 because when n tends to infinity, this part goes to 0, and it's just a singleton event. So the probability, so this singleton, this is an event, and this is an event, and this is also an event. So the closed interval AB is a union of events, so it is also an event. And we have this closed interval to be equal to plus singleton event A and B. And these are all 0, so they're equal, which is B minus A. Yeah, so this is for week 10, problem 1. And for problem 2, there's an error, there's a mistake in the question. It's not open intervals, it's just countably many intervals. So either a closed interval or one of them is closed So all such intervals. And we want to first prove that the complement of an interval is the union of finitely many other intervals. And it is actually easy to see. Just take any interval, and in the range from 0 to 1, this interval is just so A and B, and A and B is not included in this interval, and the complement of this is just from 0 to A, and then from B to 1. So the union of is just the union of 0 to A and B to 1. So it is a union of intervals. And for other closed intervals, you can show it by a similar manner. I'm not going to show it here. So the complement of an interval is the union of finitely many other intervals. We have proven this. And to prove, we want to now next prove P is well defined on F. So P, the probability is well defined on F. And since every event E, we want to prove that every event E has a unique probability assigned to it. We can see that the event is just all such intervals, and I equals to 1. So every event is an interval, and the event, I'm just using closed interval here, but it can be any, I'm just using open interval here, but you can show it using any intervals. And every event is an interval, and it's just every AI and BI and goes to infinity. So this is the definition of event. And the probability of event is just sum of every such event, the probability of the sum, or the sum of the probability of every such event. And as in question 1, this is E minus A. Yeah. So the probability here is well defined. And now we want to show SEP is probability space. As in the lecture, we want to show that SEP is a probability space. We want to show that the empty set is in E and S is in E. This is easy to see, right? Empty set is just we take any A1 equals to B1 equals to X. This is a singleton event and is empty set. And for the whole sample space, since the empty set is in the event, then the complement of an empty set is the whole sample space, and the complement of an event is also an event. So the sample space, the whole sample space S is also an event. Okay. So next, we want to show that if x1, x2 is in E, then the probability, the sum of all the events is in E. So by the definition, every such event is an interval. And yeah, this is actually trivial, as we also have shown here. The sum of them is also an event and is in the set of events. And the next one is if X is in the event set, then its complement is also in the event. And this is also trivial, as we have just proven here. The complement of an interval is a union of finitely many other intervals, and every interval is an event, and union of every event is an event. So this is true. So if X is an E, X complement is an E. And next, the whole probability of the whole sample space is 1. This is true because it's just from 0 to the sample space is 1, 0. And its probability is 1 minus 0, and it's 1. So the probability of the whole sample space is 1 is true. And the last one is if x1, x2 such events are disjoint, then the probability of their union equals to the sum of the probability of each event. And this is also true because we have the probability of each interval to be b minus a, and each interval, and by the definition, each interval a1, ai, bi, they are disjoint. So the probability of each such interval is bi minus ai, and this is just the length. It's just the length of an interval. So on this line, it's just the length of an interval. And since each interval, they're disjoint, so this is true because each interval, the probability of each interval is just bi minus ai, and they're disjoint. So this one is true. Okay, so SEP is a probability space. Yeah, and let's move on to question 3. For question 3, it is a gambler's ruin problem. You can find it on Wikipedia. And in this problem, we want to model it as a Markov chain. So we have infinitely many Markov chain. And at each state, it means that the gambler has this many money. And let's define, we want to solve this problem 3 and 4 together. Let's define the probability of, let's define the probability of losing $1. So we've moved from state on the right to the left. It means that we lose $1. In question 3, the probability is 0.6. And in problem 4, the probability is 0.5. Let's let Q to be this probability. So this Q is 0.6 in question 3 and 0.5 in question 4. And let P be the probability that the gambler wins $1. $. This is uh, 0.4 in question 3 and points, oh no, 0.5 in question 4. So the probability of losing is Q and the probability of winning is P. So notice that when the gambler is ruined, he stays here forever. And now we can write the equation. Let me first just define xn to be the states that the gambler is at after n steps. So it's just delta 1 plus delta 2 plus delta n. So this is the states that the gambler is at after n steps, and this is the move on the Markov chain of this probability of this gambler at this step. And we have x0 equals to 10 Hong Kong dollar because we start at 10. And you can see that the game will end when xn equals to 0. So maybe after some steps, after n steps, the gamblers have no money. So xn equals to 0. Now we can define tau. Let me define tau n to be the minimum of such n, such that xn is 0, given that we start at 10. So this simply means that the minimum number of steps the gambler, so the minimum number of minimum number of rounds that the gambler has to, that the gamblers take to get ruined, so gets broke. And we let this to be tau I. Then we can see that we can now define another variable. Probability I is just x. Tau I is the minimum number of steps that the gambler is ruined. And we let this probability to be that the gambler is still not ruined and has this many Hong Kong dollar. So PI is the probability that the gambler, let's say the gambler wins, so he's not broke, and has n Hong Kong dollars. So has n Hong Kong dollar where n is not 0. So it means that after this many steps, the gambler is still not ruined, and we can say that he wins. So we see that probability 0, P0 is 0 because the gambler starts at no money, starts at ruin. So he's already broke at start, and Pn equals to 1. So he already has this many money at the start, so he wins, and the probability is 1. Okay, so now we can use this PI. We can see that PI is, so Q is the probability that we lose 1 money. So Q is the probability that we lose one money, and P is the probability that we gain one money, gain $1. We can just rearrange the terms. Minus PI equals to Q over P. PI minus PI minus 1. So after rearranging the terms, we get this. Wait. Yes. So after rearranging the terms, we get this. And PI, actually PI should be P should be the probability we win $1, and Q is the probability. Yes. Okay. So by this relation, we have P2 minus P1 equals to this, 1 minus P0. And since P0 is 0 here, so it's just P1. And P3 minus P2, it's this. And we can substitute this one to here. So it's just PQ squared P1. And you can write it out. So in general, PI plus 1 minus PI equals to this. Yes. And so we have this is the sum of all, so from K equals to 1 to I, K P over P and times PI, P1. So this is the relation we have. And we can throw this term over to the right side. So it means that we add one more. Oh no, actually this term should be 1. Because here we have I and here we have 1. So the relation should follow. And we can throw this P1 to the right side. Then we now start at K equals to 0. So this is PI plus 1. And you can just, this is a so this is a geometric series, right? So we can have P1 goes to Q over P to the I plus 1 and 1 minus Q over P. This is when P is not equal to Q. When P is equal to Q, we simply have PI equals to I plus 1. This is P equals to Q, which is 0.5. This is PI, P1. This is P1. So we have this relation. And now we can substitute I equals to n minus 1. So we can calculate Pn. And Pn is 1. So remember, Pn is 1. So we have when I equals to n minus 1, we have Pn equals to 1 equals to, so I plus 1 is now n. I plus 1 is now n. This is when P is not equal to Q. And when P is equal to Q, we simply have I plus 1 is n. So this is P1 times n. And this is equal to 1. So we can swap this P1 out. So this is, we have P1 equals to and then this is 1 over n. And okay, so this is P1. This is what we have so far. This is P1. And from previous, we have Pi plus 1 equals to this part, right? So we can just substitute this P1 into here. And we now have substituted into, we have Pi. So we just substitute P1 into Pi plus 1. And we can have Pi equals to then this is I over n. So this is Pi. So Pi is the, we have defined Pi to be the probability that the gambler has I money after tall I steps. So when when the gambler takes infinitely many rounds, and eventually we see that in question 3, P is not equal to Q. So we are interested at P10. Oh, this Pi is that when we start at I dollars, the probability that the gambler gets not broke. So the probability that the gambler still has some money after tau I steps. So in question 3, we have Q equals to 4. Oh no, 0.6, and P equals to 0.4. So is n over n, and this n, it's the number of steps that the gambler takes, and when this n tends to infinity, it means that the gambler keeps on gamble. You can see that this one goes to 0. So the limit n tends to infinity, this one goes to 0. And similar for question 4, when n tends to infinity, P10. This is also 0. So this is the probability that the gambler still has some money when if he keeps on gambling. And the probability is 0, so the probability he breaks is 1 minus this one is 1. So in both questions, the gambler will gets ruined. It means that he will be broke after if he keeps on gambling. So this is problem 3 and 4. For problem 5, Zhaorun takes 2 independent samples from probability space. So call them Z1 and Z2. And he computes Z to be the maximum of them. And Xuran takes only 1 sample from the same probability, call it X1, and he computes X equals to the square root of X1. And we have to prove that Z and X have the same distribution. So we have to prove this. So we can just write Z, this is equal to maximum, because Z sets to maximum of Z1 and Z2, A. And since Z1 and Z2, let's write it this one first. So it is equal to, they are both smaller than A, right? Because the maximum of Z1 and Z2 is smaller than A, then both of them are smaller. And since Z1 and Z2 are independent, we can write it as this. So they're independent. And for a uniform random variable Zx on this from 0 to 1, we have the probability of Zx smaller than or equal to A equals A. So we have this, and it means that the probability of Z smaller than or equal to A is A times A, because they're both smaller than A, which is A squared. So this is for Zhaorun's part. For Xuran's part, we have we have X smaller than A, and X is equal to the square root of X1. And we will have X1 just square them, and then it is A squared. So they're equal. This part and this part, they're equal. And this is problem 5. So now let's move on to problem 6. We uniformly take a random permutation from the set. What is the probability that the picked permutation is a derangement? So we have learned what is a derangement. It means no element is in its own space. And what is this probability if we have infinitely many elements? So this n tends to infinity. So it is actually simple. We have learned that in previous weekly problem sets, the total number of derangement, which is denoted at this. The total number of derangement is over A factorial. This is the total number of derangement. So the probability that we pick a derangement is just this over all the all the permutation. So it's n factorial. And this is just, we don't have this part. So this is the probability that we picked a derangement. And when n tends to infinity, it is this. We have this equation, and we have a Taylor series. You can Google that or find it on Wikipedia. We have a Taylor series, which is the definition that e to the power of x, it's from 0 to infinity, x to the power of k over k factorial. This is Taylor series. And you can see that we have, for this part, we just have x equals to -1. So this is e to the power of -1. Okay, so this is the probability that when n tends to infinity. This is problem 6. And for problem 7 to 10, it's asking about Amir walking on this grid. And for problem 7, Amir starts at 0, 0, so the bottom left corner, and he keeps on moving right or up. If he has a choice, he picks uniformly, so either go right with half of the probability or go up. And he keeps on doing that until he reaches this part, which is 8, 8. So what is the probability that he never visits the red dot? So you can just find it iteratively. So every steps, Amir has probability of 0.5 to go either up or down. Oh, no, either up or to the right. So you can just compute for each step. We can define a Pij to be the probability that Amir reaches Ij. And you can write a Python program to compute that. So for example, if you're at here, we want to calculate probability of 4, 3. It is just 0.5 of probability here. This is 3, 3 plus 0.5 of probability 2. No, this is 4, 2. 0.5. So you can just write a Python program to compute it. The Python program will be provided to you in the solution. And a thing to notice is that when Amir is at this, so when j equals to 0, or when I equals to 0, so for example, this one, this is 0, 6. The probability is just 0.5 of the point that is below it. So at these two lines, the probability only depends on the lower point or the left point. So this is the corner case you have to consider. And for other points, it's just calculated as this. And you can write a Python program to calculate that. And finally, we will find the probability of reaching the red point. So it is just 0.5 of this point and 0.5 of this point. And after you find this probability, you just 1 minus this probability. So 1 minus the probability of red dot is the answer for this question. And for problem 8, so consider the same grid. R is the event that Amir visits the red dot, and we have Eij to be the event that Amir visits point I and j, so any I and j. For what values of I and j are Eij and R independent? So for Eij and R to be independent, we want to have their intersection is equal to their probability. So we want to have this relation. We can also use can also write a Python program to compute that. Oh. But let me just erase this. So we can use a strategy. We can divide this grid into 4 parts based on this red point. So you can see that for these points and these points, so it's just the points that I covered, their probability, so P, Eij, and R, you can see that if you reach these points, you cannot possibly reach the red point, right? So they have a probability of 0. And similar for these points, but the probability of Eij itself and probability of R, it's not 0. So since they're not equal, so these two parts are not equal. They are not equal. So these points, they are not independent. So these points are the Eij and R, they are not independent. And for all other points, so let's say, so for all other points, so it's covered here, here. They are also not necessarily independent, but as long as we have P, Eij, and R equals to this, they are independent, and you can just use the Python. I also have written a Python program for this. Oh no, I didn't write a Python program for this, but you can also find for every point, you can divide it into this 6 by 6 grid first, and then you calculate for the probability of each point in this grid, and then for the probability of each point in this grid. And then you see that which point have this relationship, then they're equal. No, then they are independent. So for Eij and R, you have to first calculate the probability of reaching Ij, and then you calculate from Ij the probability of reaching R. So it is the probability of first reaching EIJ and R, then first reaching EIJ and then reaching R. And for this grid, you have to first calculate the probability of reaching R and then reaching EIJ. So for all those points that have this relationship, they are independent. So next question is, Amir will take all the possible points from the bottom left to the upper right. How many times will he see a blue point? So over all his walking. One thing to notice is that you may visit several blue points in a single path. So for example, this path, it has 4 blue points and it should count as 4. So you have visited 4 blue points just in this one path. And you can calculate iteratively. So also use the strategy, so 0.5 of probability. No, we don't have to use probability for this question because we just need to count how many times we visit a blue point. So we just use for the number of paths that we visit here, it's just from previous weekly problem set. We know that it has this many paths, and then for this point, we have this many paths, and we just have to, for this point, we have to calculate how many paths are from the lower left point to this point, but it visits only one blue point. So for example, this path visits only one blue point, and this path visits 2 blue points. So we have to calculate for each blue point, the number of paths that we visited that has I blue points. So for example, for this blue point, we have to calculate the number of paths that has, for example, the number of paths that has only one blue point. So this is an example. It has only one blue point. And we have to calculate the number of paths that has 2 blue points. So this has 2 blue points because here and here we have 2 blue points, and so on. 3 blue points, and finally 4 blue points. So for each blue point, we calculate this, and then finally we will have the number of times that we see a blue point over all his walking. And you have to remember that for the number of paths that you visit 4 blue points, you have to multiply it by 4. And this is for problem 9. Problem 10, we can use, it's just the same as problem 7, except that now at a blue point, we go right with 0.2 of probability and go up with 0.8. And for red points, we go right with 0.9 and go up with 0.1. So it's just you just need to modify the Python code. I have written one Python code for you. You just need to modify in Python code that when should you change your probability in moving right or up. And for example, when you encounter this red point, so for this point, you know that the probability that you will travel from red point to this point is only 0.9. So we have 0.9 from this red point to here, and we have 0.5 from this point to go up. This is 7.75. So just need to modify your Python code to calculate the probability. And this is for this part. Okay, so now move on to week 12 problem set. For this problem, we have this part 2. It is out of syllabus. You can think of it on your own. How do we get a zero sum but not determined game? But I will not cover it here. For the first part, it's just we have learned it in the lesson, in the lecture. It's just a reachability game. It is an infinite duration zero sum and determined game. It's a reachability game. And for this two, determined but not zero sum. So we can design a game like this. So this is player 1's node, and then player 2's node. So we have to first, I want to first talk about the definition of the zero sum and determined. So zero sum, it means the objective of player 1 is the complement of other players' objective. So equals to complement of the other player's objective. So it is a zero sum. It means the objective of one player is the complement of the other player. And determine, it means that the winning set is the complement of other players' winning sets. Okay, write it like this. The complement of other players' winning set. Yeah, so this is the definition. And for part 3, we want to have a determined but not zero sum game. So let's consider this game. It is definitely determined, because if we start at this node, player 1 can keeps on staying at this node. So he can stay at node 1, vertex 1, infinitely many of times, and similar for player 2. But it is not zero sum, because if you consider a path that player 1 takes, this edge to node 2, then this path is not in any player's objective path, right? Because for player 1, his objective path is to stay at vertex 1. So take this edge infinitely many of times. And for player 2 is like this. But as long as player 1 takes this edge is not in any player's objective path. So it is not zero sum, because the objective path of, so there's a path that is not in any player's objective path, like this. So that the objective path of player 1 is not the complement of the other. So it is not zero sum. Oh, actually, let me write. Never mind. So for the game that is neither zero sum nor determined, we can have this game. So if you consider this game, player I is forced to take So player I is forced to take this edge to player 2's vertex, and then player 2 is also forced to take this edge to player 1's vertex. And they cannot stay at their own vertex infinitely many of times. So it is not determined because the objective path of both player is 0. No, it's empty set because we have to go to the other player's node. We are forced to go to the other player's node, so it is not zero sum, and this path is not in their objective path, so it is not zero sum, and it is also not determined. Okay, so now let's consider problem 2. It is a zero-sum 2-game infinite duration game on a finite graph where player 1 has T1 and T2 sets of vertices, and his goal is to visit both of them. So is this game determined? We will show an algorithm that finds the winning set. It is determined, but we can prove it by showing the algorithm. If we can show an algorithm finding the winning sets, then it is determined. And is it memoryless? No, because consider this game. Consider this game. So this is in node 1 is in T1 and node 2 is in T2. And the goal is to visit both vertex 1 and vertex 2. But if we can have a memory, we can't have a memoryless strategy, because if we don't remember, for example, whether we have visited nodes in T1, then in this game we may take an edge from vertex 0 to vertex 1, and then we stay at vertex 1 forever, since we don't remember whether we have visited T2. So we can take an edge to T1 and then stay here forever. So we cannot have a memoryless strategy. Okay. So part 3, let's design an algorithm that finds the winning sets for player 1. So we can create 3 copies of the game. 3 copies of the game. Copy 1. No, copy 0. Let's say copy 0. Copy 0 is defined. So let's consider this game. This is copy 0. And we want to have another 2 copy of the game. This is copy 1 and this is copy 2. So now for every vertex in T1 of copy 1. So for example, T1 of copy 1 is this vertex. We want to add an edge. So you can see that in this original game, we have an edge to itself, and we have an edge to vertex 0. So this is T1, and this is copy 1 and copy 2. So for this vertex, we want to, since it has an edge to itself and 0, node 0 in copy 0, so we want to create an edge to vertex 0 and also create an edge to vertex 1 here. So this is similar for this one, because we have an edge to itself and an edge to vertex 0. So we create an edge to vertex 0 and vertex 2 in copy 2. So now, if you start at here, start at the original copy of the game, and you try to visit T1 and T2. So for example, if you visit T1, you can now take this edge to the copy of you can take this edge to the copy of copy 1. So you can take this edge to copy 1, and then you start this game at here. And then you start this game here, you can try to find a node in T2. And similar for here, for example, you start at vertex 0, and then you go to vertex 2. You can take this edge to vertex 2 and then start this game at a new copy. So the strategy is to, no, the algorithm is to, if there is an edge UV in copy 1, no, copy 0, the original game, if there is a copy in original game, we add an edge that is in copy. No, we add an edge. So if U is in T1, we add an edge to V in copy 1. If there so we add an edge to copy 1. Otherwise, we okay. So for here, originally we have a edge to itself and an edge to vertex 0. So we add this to edge, and similar for this one. So for in this 3 copy vertex, so copy 0, it means that we haven't visited neither, so either vertex in T1 or T2. We have visited none of them. But as long as we visit one of them, we can take the edge to another copy, or from T2 to copy 2. So to another copy, and then we start the game there. And then start the game at this vertex there in the copy, another copy. And we keep on finding, so in copy 1, it means that we have already visited the vertex in T1, and we are trying to visit a vertex in T2. And for copy 2, it means that we have already visited a vertex in copy 2, and we are trying to visit a vertex in copy 1. No, in T1. So this is the algorithm, and yeah. So for the fourth part, let win1 be the winning set of player 1 in the game above. Suppose that win1 is the winning set of player 1 on the same arena, if their objective is visiting T1. And V2 is the winning set with objective T2. Do we have this equation? So no, because of the same reason that we explained here. So consider this game. If we start at 0, the winning set of player 1 is that we can take an edge to T1. And then the winning set of T2 is that, so for winning set win1, 2 is that we can take an edge to T2. But win1 is the set where we can take the edge to T1 and then back to T2 and then take another edge to T2. So it is not equal, because win1 we just need to take an edge here and then we stay here. Win2 is we can take win1, 2 is that we can take an edge here and we stay here. But win1 we must take an edge to vertex 1 and then back to vertex 0 and then to vertex 2. So they're not equal. This is problem 2. So for problem 3, the game is a little bit different. We want to visit T1 and T2 infinitely many of times. Is this game determined? I will provide a algorithm for finding the winning set. And do memoryless strategies suffice? No, because of the same reason here. Because we have to remember whether we have visited the vertex in T1 or T2. So now I'll give an algorithm for finding the winning set. So let's consider this arena, T1 and T2, and we may have some edge. So there are sets of vertices. We may have some edge going out of T1 or T2, and we can also have a copy of this game. And because we want to we want to visit T1 and T2 infinitely many of times, if we visit, so we can create an edge. So for every vertex in T1, we can create an edge to the second copy. And then for every vertex in T2, in the second copy, we can create an edge back to copy 1. So this is copy 1 and copy 2. So we see that now, if we start at the first copy and we visit a vertex in T1, we will go to the second game. And then from the second game, we will keep on looking for T2. And when we find the vertex in T2, we'll go back to copy 1. And then from copy 1, the set of T2, we keep on finding a vertex in T1. And then it keeps on going. So in this way, we will find a winning set that can visit T1 and T2 infinitely many of times. So yeah, this is for problem 3, the algorithm for finding the winning set. And for this part is the same reason as problem 2. So this part, this is not true. Okay, so for problem 4 and 5, consider this time we want to visit T, but avoid visiting F. So is this game determined? We'll prove it by finding an algorithm. Does memoryless strategy suffice? Yes, because this time we only want to look for the vertex in T, but not in F. So we just keep on looking for T. So now I'll give you a strategy, an algorithm for finding the winning set. So for every vertex in F, we want to avoid visiting it. So in the original game, you may have some edges going out of F. Now we want to remove these edges, and then we create an self loop. So if we visit a vertex in 1, we're stuck here. So we cannot go anywhere. It means the game it means the game ends. So for this game, it has now been transformed to a reachability game that from lectures, we have learned from lectures. It is a reachability game because now we only want to visit vertex in T, but not vertex in F. So because as long as we visit F, we will stay at F forever. So we'll avoid visiting F. So it is now a reachability game, and you can apply the algorithm learned in the lecture. So this is problem 4, and problem 5, we want to visit T infinitely many of times, but visit F only a finite number of times. So this is game determined. We'll provide an algorithm. Memoryless strategy suffice because of the same reason in problem 4. So the algorithm for problem 5, let's still consider a game arena. This is F, and second copy. This is F. And for this set, we want to have the vertex that is in player 1's vertex. So because we are player 1, and we want to visit T infinitely many of times. So this is also vertex, player 1's vertex. So now we want to visit T infinitely many of times. It means that we want to go from a vertex in the first copy to the second copy. And for the vertices in the second copy, we can also use the same algorithm here. We can remove all its outgoing edges, and then we create a self loop. So if we reach this reach this set, we will stay in F forever. But for the F in the first copy, we will not modify it. So now, if we start at here, we can visit F, and then we go out of F, and we can keep on visiting other edge, and we can visit when we visit a vertex in player 1's vertex, and player 1 can choose whether he wants to go to the second copy. And the thing is that if player 1 chooses to go to the second copy, then in the second copy, it is the same reachability game you have learned in the lecture. We have transformed here. It's the same reachability game. We want to avoid visiting F. So as long as we visit F, we will stay in F forever. So from here, it is the same reachability game. So the thing is that for player 1, he has to keep visiting vertices in the first copy, and then when he decides he don't want to visit F anymore, because in copy 1 he can visit F, but as long as he decide he doesn't want to visit any F anymore, he can take the edge to the second copy, and he keeps on visiting T in the second copy. So this ensures that player 1 only visits F for a finite number of times. So this is problem 5. Problem 6. We will consider a variant of the game of NIM with 2 heaps, in which the player who cannot make a move wins. We want to find the winning and losing positions. It is actually the same question that is covered in week 2, I think. So it is the Messier NIM game. You can search it. It's a Messier NIM game. The losing player is the one that is forced to make the last move. So we can see that a player who reduces the last number to 0 is going to lose, because if he reduces the last number to 0, then the other player cannot move, then the other player wins. And we want to show that a NIM sum, which is the XOR of the numbers, the NIM sum of 0 is the winning position for player 2. So player 2 starts, it's a losing position for player 1. So player 2 is the one who starts the second. Player 1 is the one who starts first. in the lectures you have learned that it is also true that a name sum of 0 is a winning position for player 2. So now let's consider two numbers, I and j. Player 1 move first, and we can see that a name sum of 0, it means that I is equal to j, right? It means that I equals to j, and I and j are larger than 0. So they are larger than 0. So we can have three situations. One situation is that player 1 reduces I to 0. Reduces I to 0. Then player 2 can reduce j to 1. Then player 1 must reduce j to 0, and player 2 wins. Player 2 wins. And the second situation is that player 1 reduces I to 1. Then player 2 can reduce j to 0, and player 1 must reduce I to 0. Player 2 still wins. Right? So now if we don't reduce, so we want to reduce to a situation that so both I and j are not 0. So let's say player 1 reduce I to I by x. No, just reduce I to n. So I now equals to n. Player 2 can use the strategy that is taught in class to copy player 1's move. So he will reduce j to n. And in the end, we keeps on reducing the number, and player 2 keeps on copying player 1's move. In the end, we will have player 1 reduce I to 1, and player 2 reduce j to 1. And you can see that player 1 we will have a situation where player 1 can reduce I to 1, and then player 2 reduce j to 1. Actually, this time player 2. No, actually this time player 2 wins. No, player 1 wins. Player 1 will reduce. Oh, this is the corner case of this Messier name. So this time player 1 will reduce I to 0, and player 2 must reduce j to 0. This time player 1 wins. The state of 1-1 is actually a corner case for this game. You can see that when the state is 1-1 and player 1 starts first. Player 1 starts first. In this case, player 1 wins because he can reduce one number to 0, and then player 2 has to remove another number to 0. Player 2 makes the last move. Player 1 cannot move, so player 1 wins. But for all the other cases, player 2 can keeps on copying player 1's move. So because we will not have a situation that when player 1 reduce one number to 1 and player 2 still reduce another number to 1, because if you see player 1 reduce a number to 1, player 2 can directly reduce. So it's the same case as the second case. Player 2 can reduce another number to 0. So he doesn't have to copy player 1's move this time, and player 1 still lose. So for this case, if player 1 does not remove I to 0, so player 1 does not make the game state so that one of the number is 0, player 2 still wins, because player 2 don't have to copy player 1 to the end. And 1-1 is the corner case. We have this same conclusion that when nim sum is 0, so this is from the class, when nim sum is 0, it is a losing game state for player 1, except for 1-1. 1-1, we also have a nim sum of 0, but it is a winning state for player 1. And for problem 7, it is similar. Problem 7, it is similar. We just have to consider, so for all the nim sum part, they are the same for problem 7, except that for the all numbers from A1 to AK, for all the numbers, arbitrary number, we have to see then how many, so if this number is even, so if we have A1, A2, all the way to AN, where N is even, you can see that, so let's consider 4 number. They're all 1, because we only consider the corner case 1. They're all 1. So player 1 will reduce this to 0, player 2 reduce this to 0, player 1 again reduce another to 0, player 2 reduce to 0, and player 1 wins. So you see that if there are even number of heaps, then player 1 wins. If there are odd number of heaps, then player 2 wins. So the extension is that we still have a nim sum of 0. We still have this conclusion. But the number of heap, when all the heaps, when all number is 0, no, is 1, the heaps we must have even number of heaps. So this is the extension. For problem 8, we want to design a one-shot game with finite number of players that does not have a mixed Nash equilibrium. To do this, we have to have a situation that so they don't have a mixed Nash equilibrium, so we must provide both players with the finite players with infinitely many strategies. So consider this game, the player A and B. The thing is that they each provide a number within this range, and the player that provides a larger number will get a reward of 1. So this is the payoff table. But when they have the equal number, they have 0 payoff. So when XA is smaller than XB, so this is the number they give. When XA has some smaller number, XB have a payoff of 1, and vice versa. And when the two numbers are equal, they both have 0 payoff. So you see that in this case, both of them will give as large number as they can. So they may have 1, so they may want to give 1, but if they give 1, then the numbers are equal, and they both get a payoff of a 0. So they want to have as large a number as possible. So for example, if player A gives 0.99, then player B can always give so 1 digit larger than player 1's number, and it keeps on going. So we have infinitely many strategies for both players, and they don't have a mixed Nash equilibrium. So this is problem 8. So for problem 9, we want to show that which one is larger, the set of games that have exactly one mixed Nash equilibrium, or the set of games that have infinitely many mixed Nash equilibrium. We want to show that they are equal. And so we have to find a bijection between A1 and A infinity. So let's first do it this way. The thing is that we can add one new strategy for each player to create, but we have to keep the payoff same. And this will create infinitely many meshed equilibrium. So consider the matching pennies game. But instead of head and tail, I use A and B to represent. So this is for player 1. This is for player 2. And so when they all have A, the payoff is like this. So this is from the lecture. The payoff is like this. And you have learned from the lecture that the mixed Nash equilibrium is that they give A and B with equal probability. So they have PA 0.5, PB equals to 0.5. But now if we add another strategy that does not change the payoff, you can see that we just need to have AB plus BP plus PC equals to 1. And since C does not change the payoff, we still want to have PA equals to PB. But PC, we can set it to anything. So as long as they add up to 1. So for example, we can set PC to be 0.1, then PA and PB will be 0.45, and similar. So if PC is 0.2, then payoff, not the probability for A and B is 0.4. So you can see that we have infinitely many mixed Nash equilibrium here, because there's one strategy more, one more strategy. And for the reversed direction, A infinity to A1, again, we will add the strategy. The thing is that we can add one more algorithm that has more payoff than the largest original payoff in the game. So we can add one more strategy. So here we can use this game because this game is now have infinitely many mixed Nash equilibrium, right? Because we just transformed it to have infinitely many. So we add one more strategy for both player that has a payoff that is higher than the largest payoff existing in this game, this original game. So you can have like this. So the payoff table is now looks like this. If they both give out B, then we give them a reward of 5. you can see that the mixed Nash equilibrium is for both player to play D. So yeah, they will have D equals to 1 because this maximizes their payoff, and we have only one mixed Nash equilibrium. So this is from A infinity to A1. And since we have A infinity one-to-one function from A infinity to A1, and we have the A1 to A infinity, so they're equal. Okay. For problem 10, the last problem. So suppose n people are taking part in an auction to buy a valuable item, and each person will have a valuation in mind. So person I will think that it's worth VI value, and BI is the bid that they give, and CI is the money that they pay. The payoff will be, of course, VI minus CI if they win the auction. If they lose the auction, they don't get anything, they don't lose anything, so their payoff is 0. And in the so first part, in the normal auction, the player with the highest bid wins, and they will have to pay exactly their bid. So we have CI equals to BI. Would a rational player always use their actual valuation as their bid? So will they always bid BI equals to their valuation VI? The answer is no, because consider if I want to win this auction, I want to maximize my payoff. So I want to pay as less as possible to get the item that I want. And if I think that the other participants don't think that this item is that much valuable, so if I think that this item worth $100, but the other participants may not think that way. They may think that this item only worth $70, $70 or something. Then the bid that maximizes my payoff is to bid $71, because in this case I only have to pay $71. So a rational player they may not have may not have BI equals to VI. But in the second part, in the second prize auction, the player with the highest bid wins, but they will only have to pay the second highest bid. In this case, would a rational player always use their actual valuation? In this case, yes, because suppose bidder I is the highest bidder, we can either increase our bid or lower our bid. So if I increase my bid, my payoff decreases because, of course, I bid. If I'm the highest bidder, of course. Oh no, if I am the highest bidder, if I increases BI, and my profits will not change because I only have to pay the second highest bidder's bid. So it doesn't matter if I increase my BI, my bid. But if I decreases my BI, it also does not change my payoff because I only have to pay the second highest bidder's bid. So in each case, in any cases, I only have to bid the second highest bidder's bid. But if I am not the second, so in this case, I will bid my actual valuation, because either no matter how I increase my bid or decrease my bid, if I'm the highest bidder, I always have to pay the second highest bidder's bid. But if I'm not the highest bidder, so suppose I'm any bidder that's not the highest bidder, if I increases my actual valuation, if I increases my bid higher than larger than my actual valuation VI, then my profits will decrease, because if I increase my bid and bid more than my valuation, if I still does not become, if I still no, how do I say? So if bidder I increase his bid, if he is still not the highest bidder, he does not have to pay anything. So his payoff is zero. But if by increasing his bid, he becomes the highest bidder, he has to pay the second highest bidder's bid. And in this case, because I bid more than my valuation, then my profit, my payoff will decrease because I have to pay more. But if I decreases my if I'm not the highest bidder and I decreases my bid, my profit does not change because I will not win anyway. So in this case, if I'm not the highest bidder, I still have no payoff in increase in payoff to adjust my bid. So I will bid also my valuation as my bid. So this is for problem 10. In second price auction, all players will actually rational player will use their actual valuation as their bid. So this is for problem 10.